Hello and welcome to this new video. Today we are going to talk about the Linux kernel 6.10. We have big performance gain, we have new profiling tools, we even have a commit from prison, and much more coming up. As usual, we will start by reading Linus Torvalds' message. So he tells us that in the last week, in the final week, it was a little bit more heavy than usual. So it was a little bit more scary. Of course, when there's more commits on the last week, it's always weird because you don't have as much time to test them. So it's a little bit scary, but still, it wasn't that much that it warranted an extra week. Now, we're getting in the summer, so the next release will probably be interesting to see if there's going to be a lot of change or if it's going to be a small release. But for now, let's stick with the 6.10 that we're starting now. Now let's start by talking about architecture-specific changes, more precisely about ARM64, which now has support for user fault FD, which is a page write protection command. Now, for all of the news, for all of the change that we see to the kernel, I'm going to divide every concept that we don't already know to make sure that everything is as clear as possible. So let's start by talking about the command in and of itself, user fault FD, which the user at the start tells us that it can be run inside user space. Now, inside Linux, there's two different space. There's kernel space and there's user space. Now, kernel space is pretty much an internal command that only the kernel or kernel function can use. So it's something that you cannot use as a standard user. You cannot use it to make an app. You can only use it if you're inside the kernel. And user space is pretty much everything else. So if you create an application or a program, you can now use this user fault FD even on ARM64. Now, what does page write protection mean? Pages are part of memory. So when your program needs memory, the kernel will give it pages. Now, pages are just a small block of memory that your program can use, and write protection, of course, means that you can ensure that nobody will write that memory. Now, user fault FD is really interesting because it's way faster than other tools that you would normally use to do write protection. So good, ARM64 now has it. Now still talking about ARM64, which now has faster linear map creation. Now what are linear maps? Linear maps are something that is created at boot to pretty much split the memory. So the bigger your memory, the more linear maps you have. So optimizing them is really crucial to be able to optimize your boot time. Now, they managed to do a 50 to 95 performance gain on it. How did they achieve that? Well, they made a lot of change, but one big change that they made is that now TLB invalidation were reduced to be only used once instead of multiple times. Now, what does that mean? First of all, TLB stands for Table Look Aside Buffer. Now, remember those letters because a table look aside buffer is one of the most important things for optimization in the Linux kernel these days. We see it pretty much everywhere. Now, what it does is pretty much help your CPU be faster at finding things in memory. Because normally when you want to find something in memory, your CPU kind of has to search it a little bit. It can be slow, so it tries to find it in memory, and when it finds it, oh yeah, I got it. Now, for us, it might always feels fast, but it's not always fast for the CPU. So the CPU has kind of a cheat code to make sure to remember where things are and to be able to be as fast as possible. Is it puts some information that points where the thing is in the table look aside buffer, which is just a little part in the CPU in really, really fast memory. So optimizing what goes there and making sure that what goes there is as optimized as possible is really important. And when we do a TLB invalidation, what we're doing is pretty much removing data from that table look aside buffer. Now, invalidation are something that are fairly slow, so reducing them as much as possible is really important, and turns out it was doing it a couple of times when you were generating those linear map. So being able to reduce it to 1 makes it way faster. Now, like I said, there's a lot of change aside from that, but it's still really impressive 50 to 95% performance gain. Now let's switch to 32-bit ARM that now has support for CFI, which is Control Flow Integrity. Now, what is Control Flow Integrity? Well, when two parts of the kernel want to talk together, they will use indirect function call. Now, they kind of have a return address inside them that tells them, hey, if you want to throw data at the end, just throw it back there. Now, if you were an attacker, you could look at this and just change that return address to make sure that the information comes to you instead of the function that you really want it to be at. So the way that they solve this is that they make sure that all the address that you can return stuff from or stuff to will be checked by a jump table. Now, jump table are a whole thing in and of themselves. They're pretty much magic that can be generated at compile time. So because they need to be generated at compile time and they're not something that you can just code into being, you need a special compiler. So people that want to use this will need to use clang for it. And if you wanted to know, well, if you, after having CFI enabled, manage to change a return address that you're not supposed to, it will do a kernel panic, which is pretty logical because if somebody has that level of control over your system, you really want that person to be out of your system and to close the system to make sure that no data is stolen or that you don't have any more issues. Now we can continue with BPF just-in-time compiler that has been added to Arc V2 CPUs. Now there's a lot to explain there. So let's start by the BPF just-in-time compiler. Now BPF stands for Berkeley Packet Filter. So what the Berkeley packet filter does is it can take either a file or a socket and it will stay there and receive information from it and be able to treat that information to send it to a program or to do something with it. Now, it's a pretty simple program, but it allows to do a lot of things. It allows you to do benchmarking, to do networking, to do security, because you can have information from a lot of places at once. So adding that support to architecture is really important. Now, Arc V2 CPUs are a pretty weird architecture that we don't hear often, and it's normal, is because it's something that's used more in the automotive or IoT devices, or even I read that some SSDs add this technology. So it's not something that you will use, it's something that some of your device will use, and it's something that is getting, well, a little bit old. I've seen some documentation talking about 2013 when it may be released, because those kind of architecture are a little bit of a ghost. It's hard to find documentation talking about it. It's hard to find what they're doing in their life. So yes, it's a pretty old thing still. It's important to see BPF being added a little bit everywhere just because about how powerful it is and how much things we can do from it. And it's something that we're going to see throughout the changes in the kernel. And our next changes is actually related to it. We have PowerPC that now has, well, an extension of BPF that has been added. We're talking about kfuncs. Now, kfuncs is a short for kernel function. Now, what those kernel function do is pretty much an extension of BPF. So normally BPF can do simple things with your packet. It can throw it somewhere. It can modify a little bit the data and do something else with it. But if you want to do something a little bit more complex that would use a kernel function, well, you're kind of out of luck because it doesn't have access to anything. Now, because there is now support for kfuncs, you can do way more with your packet. You can modify it further and you can have information from other sources. So it's really important. And we also see another thing that has been added that we see more and more. It's Rust support that has now been added to RISC-V architecture. Now, Rust is all the craze in the kernel since it has first been added. So we see more and more part of the kernel being written with Rust in mind. So seeing more and more architecture being able to be compatible with it means that devs can now more freely make change to the kernel using Rust, knowing that it will apply not to only some architecture, but to apply to all of them. So it's really important to see those change. Now turning to something that we know a little bit more, x86 that now has faster AES XTS encryption. Now it's used for disk encryption, but the way that they made it faster is by making sure that the CPU, if compatible, so for more modern CPU, can eat more bits at a time. So normally when you use the encryption part of your CPU, it won't eat only 64 bits of data at a time. It will eat way more to make sure that things are faster. Now, I don't remember the quantity of bit that it changes, but if you're on a more modern CPU, you're not only throwing like 128, you're throwing 256 at it. Now, it doesn't do that much of a change performance-wise. I read about 5%, but still, it's fun because we're using something that was already there and gives us better performance for things that we use pretty much every day. I mean, disk encryption is a standard now. It's getting more and more important, especially on laptops, so it's good for us. And now let's turn to something just a little bit different, which is the x32 subarchitecture. Now, subarchitecture, the sub is really important because it's not an architecture. It's, well, the only way that we can describe it is really subarchitecture. So it's when you're running a 64-bit machine as 32 bits. So when you're faking a 32-bit machine, you now have support for shadow stacks. What are shadow stacks? So shadow stacks are a copy in memory that is there in order to detect that nobody messed with it. So if you compile your program and you make sure that it's enabled in your CPU, you can actually compare while running your program, hey, did somebody touch my memory while I was doing nothing with it? So it helps making sure that nobody disturbed your work. So again, it's a kind of, we could say, write protection, but now it's more of a making sure that nobody's stealing or is doing anything with your things. So again, a good thing to add. So we've been talking about a lot of things that were added. Now we're going to talk about things that are dropped. More precisely, the support for some DEC Alpha CPU. So DEC Alpha being the architecture, and the CPU that we're talking about are EV5 and earlier, which is the type of CPU. Now, the reason why we're dropping support for those is because they lack standard function like byte and word operation, which are pretty much basic for any CPU architecture, weren't there with DEC Alpha, EV5s, and earlier. So it just makes sense to drop them because it makes everything hard because we still need to support them. Remember, if they're inside the Linux kernel, we need to keep them in mind and to make sure that all the code that's written works with it, which makes everything complicated knowing that it's the last architecture with that issue. Now, even if it's an architecture that had some issues, Linus really liked it. It's one that he worked extensively with it, so he had some some words to say about it. Let me use this word because they're really well said. He says, so while it's a bit sad to see the support for my first alpha go away, if you want to run Museum hardware, maybe you should use Museum kernel. Thank you, Linus. Absolute unit of a quote. So now let's switch gear and talk about core kernel changes. And let's start by talking about some changes to mmap. Now, mmap is a tool that is made to make a map, a pointer, to some memory address. So what you want is, let's say that you want to, modify things on an hard drive. What you can do is use mmap, map the hard drive to a specific memory addresses, and now be able to exchange data with it through that pointer to that memory address. So it's a really useful tool to be able to interact with any file, with any I/O device. So it's really important that it exists. Now, they've added support for ring buffers. Now, what are ring buffers? Ring buffers are special kinds of buffers, special kind of memory that pretty much loops around, meaning that when you're writing to it, let's say that you're writing on it, oh, it's full. When it's full, it will loop back around and it will start either writing back on the same memory address, and if there's something, it will pretty much override it. So it's something that used in the kernel at multiple places. One of the places that it's used is in the log when you're booting. So when you're booting at the start of opening the machine, you actually have nothing to write on the disk. So while you have nothing to write on the disk, well, your system will store its log into that ring buffer. So that's one place where it's used, but it's used elsewhere. We're going to see it a bit later because we have some commands that use it. So we're going to be able to look at it. And now let's look at the initial step of unification for huge TLBFS. Now, what does that mean? What is huge TLBFS in the first place? Huge TLBFS was the first way that we could use huge pages in user space. Now, we know what user space means. It means the user can actually use it, and huge pages. So pages, remember, is a part of memory, but that part of memory is pretty much at always a standard size. It will always be 4 kilobyte. Now, if you need to store something really big, let's say you need to store 1 gig of stuff. Before, you kind of needed to just make 4 kilobyte pages until you got to 1 gigabyte, which is a little bit insane to do. So the way that they pass around that is that they made pages that could be bigger. So you could make a page that was 1 gigabyte, and huge TLBFS could actually let you mount it from user space and making you able to use it. Now, that's all something that's not really used anymore because, well, we can do it transparently. Right now, we have something that is called transparent huge page, which is pretty much the kernel seeing that, hey, he requests 1 gig of memory. Let's just make a page that's 1 gig wide, and it's going to solve it. Now, you may ask, why is it that much of a problem if we have thousands of 4 kilobyte pages? Well, it actually goes back to the TLB, so the table look-aside buffer, because the more pages that we have, the more we fill the table look-aside buffer. So that's actually an issue because, well, if we fill it out, we slow down our system. So having huge pages can deliver huge gain. You can, well, that's pretty obvious because, well, you would need thousands upon thousands, if it's not million, to be able to fill 1 gig with 4 kilobyte pages, but you only need 1 to do it if you have a 1 gigabyte pages. So that's where the gain is. Now, let's go back to the start of this, which was unification of huge TLB. Now, what does unification means? Huge TLBFS was made in a time where, well, we didn't have transparent huge pages, so we didn't have standard code to be able to treat this issue. And now, because we have standard code, we want to merge the two together. So make sure that we keep that support for huge TLBFS, but also be able to reuse code from transparent huge pages, because if we want to update transparent huge page, we don't want to let huge TLBFS behind. We don't want to have a part of the kernel which isn't updated, which is kind of forgotten and maybe works, maybe doesn't work. We want everything to use some standard function that we can only change the standard function to make change on everything. So that's what unification means, is because it has 10 sub-function within huge TLBFS, and now those sub-function that only huge TLBFS were reduced to 2. So most of those sub-function could be recycled and used from transparent huge pages. So that's actually a huge gain in the quantity of line of code that was deleted, but also a huge gain in how we're going to be able to service that code in the future. Now, talking about easily servicing code, we have NT-sync, which will in the future provide a set of Windows NT synchronization primitives. Now, that means a lot, but what it means in practice, so synchronization primitives are what we would call mutexes. So mutexes are things that can block your thread, your core, from doing an action because it has shared memory with another core. So it has fast user space mutexes that are usually used in Windows games. So if you have, now let me bring that around because that's a little bit complex. If you have a Windows game and you want to run it on Linux, well, right now, Wine is doing a lot of job to try to emulate what the kernel is doing in Windows. Now, when you're doing that, you're kind of losing performance because Wine isn't the kernel. Wine is a layer above the kernel. So it has kind of a slowdown there. Now, if we have a part of the kernel that is there to accept Windows command, it can use those information and make it faster and make a better, faster implementation of something that is already working on Windows, but we want it to work on Linux. So Windows game, when you're going to emulate them, they're going to be able to use those fast user space mutex, which if they're used on your Windows game, they're going to be able to be better emulated because we're passing through the kernel and not through Wine to be able to manage them. So that's actually a big win, and some people don't see how important that is, but it's important on more than just a performance front. Because yes, passing it through the kernel gives you more performance. That's good. That we're all happy about that. But there's also a whole aspect of making it easier for a dev to port their things to Linux. Because think about it. When you're making an engine or a library to be able to support anything display-wise or gaming-wise, you don't really think about Linux. You only think about Windows. So when it comes time to making things Linux compatible, while making that process as easy as possible from the Windows base is really important. Now, some engines do this better than other, but making this as fast and as easy as possible can help us have a better compatibility. Just think about it. If you're a dev and you need to port something to Linux and you can use exactly the same command that you would use on Windows, everything becomes way easier. But if you need to do a whole new integration and a whole new way of doing exactly the same thing but just in the Linux way, now you can have a bunch of bugs, you can have a bunch of issues that aren't really going to get taken care of because you're pretty much looking at your second-class citizen. You're looking at Linux, which doesn't have enough people using it for gaming for you to justify putting money to solving the issue. So it's really great that we see more and more some Windows function making their way onto Linux because, like I said, we can have more performance and bring better support to Windows devs. Now we talked about Windows and Microsoft. Now let's talk about a little bit of Google and Chrome with mseal. Now, mseal allows you to seal a part of memory. By sealing, I mean forbid pretty much everybody from changing the memory at a given address space. Now, why would you want to do this? It makes sense when we're talking about Chrome. Let's say that you want to sandbox your Chrome, you want to make sure that nobody can edit it, you want to make sure that even if you have the most cancerous, dangerous thing running on your Chrome, you don't want it to change the core of your Chrome, because your core of your Chrome will have access to everything else running on your system, and it will have access also to every other page that you have, so you really don't want your core Chrome to be affected by anything. With mseal, it allows Chrome to say, hey, never touch that memory, never touch that part because it's so important, I don't want nobody touching at it. So that's actually really great that we now have that command. Now, there was a lot of debate because people were saying that it was kind of useless or that it was that it could be done using other command, but it ended up that we did it. So good for us, I guess. Now we're talking about things that we did. We're going to talk about things that do nothing. So no print k, which was a command to do nothing. So normally you have print k when you're making drivers, when you're doing code for Linux, for the Linux kernel. It's possible to use print k to put things into the logs. So if you want to log some information, you can put a print k statement and it will do it. But now, what if you don't think that it's that important to log thing, but you still want to have a log statement there so that if you want to for example, debug your system, well, you can just change that part of your code and have some debugging that you can now see. Well, that's when you're going to use noprint. So noprint is really only there as a placeholder for a potential print statement. So it's not supposed to take space anywhere on the compile code or on the image of the code. It's just there to be a placeholder in your code. So the problem was that, well, it was taking places. So for some reason, it was taking place on the image, pretty much taking place for nothing. So they actually patched it to make sure that it wasn't using place nowhere because, well, it's only a placeholder. Good that they fixed it. Now let's introduce some more unique verbiage. We have BH work queues, which can now be enabled and disabled. First of all, work queues are queues that are there just waiting for something to happen. So let's say that you're waiting for your USB key to be plugged in. You can have a work queue that's there for that. Now, the reason why being enabled and disabled is important is because there are a lot of implementation of work queues, and there are the old implementation, the new implementation, the newer implementation. So what we want to do is to actually push to newer implementation the old implementation. The old implementation was called tasklet. Now tasklet is something that more and more is legacy. We don't really want to use it. So having this enable disable feature for BH work queues, which are the newer work queues, makes it so it's compatible with tasklet. So we can now make the code to start transferring tasklets so that they can be just BH work queues and never use tasklet again. So that's a good thing. We're going to be able to make optimization and standardize more code, not use like 15 implementation of the same thing to do something, just have one good implementation. And if we're still talking about work queues, we can talk about BPF, so Berkeley Packet Filter, that now can use those work queues, those wait queues, and they can now also enable and disable preemption. Now, the reason why it's important to be able to use those wait queues is because you would normally, if you would want to wait for something, you would need to make a whole program in user space or in kernel space if you're crazy enough to be able to just look at that thing and wait. So of course it's a huge waste, it's something that we don't want. So now that BPF can use those wait queues, it doesn't have to make a whole new implementation for it in user space. You can just use the kernel implementation and make everything simpler. So now you can wait for that USB key to be plugged in and now execute your code, which just makes sense. And enabling and disabling preemption. Let's start by what is preemption? Preemption is the capacity of being able to just cut your code while it's running. So if you're running code and preemption is enabled, you can, while the code is running, just run some more important code. So being able to disable that is important because let's say that you have something that is really time specific. If it doesn't run now, it's going to have big issues. Well, now you can say to the system, hey, don't cut my thing because my thing is really important. So that's a good thing. It makes time important process be more special in the kernel's eyes and make it sure that nobody cuts it. Now we also have a new memory allocation profiling subsystem that has been added. Now memory allocation, that means allocating memory. We can now see how much memory is allocated per specific part of the kernel and see if there's any memory leak, see if it's using too much memory for some reason. Now there's been a lot of problem adding this to the kernel because their first implementation wasn't that optimized, so there was some people saying, hey, we don't really want that in the kernel, it's not good enough, but they reworked it and made it work perfectly. So now everybody agrees this is a tool that we want, this is a cool tool, so now it's been added and devs will be able to use that tool to better optimize memory. And now we talked a little bit earlier about Rust having more and more implementation. Well, Rust now has a time handling abstraction that has been added. So when we're talking about time handling, you can think in your head timers. So there's more and more parts of the kernel that are being rewritten and made to better work with Rust. And time handling was one in this release. And now to continue to talk about Rust, but let's talk about the software version of Rust that was upgraded. So now you will need the 1.78.0 version of Rust to be able to compile the Linux kernel. Now the reason why we make that upgrade is because the new version now has a better version for the alloc command. Now the alloc command, before we used an actual fork in the Linux kernel to be able to use it, because the command that they used before in the Rust code wasn't working with the Linux kernel. So now that they have the new implementation inside of the Rust code, we can now cut 10,000 line of code that were used to make that new version of alloc. So good, 10,000 line has been cut. Now let's switch to network changes. And let's start by talking about zero copy send operation, which there's a lot to talk about it there. So first of all, what are zero copy operation? Zero copy operation are operations that are there to bypass the CPU. So when you normally want to transfer data, you transfer data by throwing it at the CPU, and the CPU takes it and throws it at the right place. Now that's slow because you need to pass all of the information through your CPU. If you're optimized, you will take, let's say, your network card, and you're gonna just give it the address and tell it to go take it itself, to make everything faster and to allow you to run something else on the CPU while you're transferring things. So let's go back to the update. Zero copy send operation using IO uring are now faster. And just by the way, IO uring is a function that's there to talk to the network, to talk to sockets, but it's also a function that uses the ring buffers that we were talking earlier. It uses 2 ring buffers inside of its implementation, so that's another place where we can see those ring buffers. So it's not only faster, but it can also use multiple buffers at the same time. So now you don't only have to send one buffer, you can send multiple buffers and tell it, just send it where you need to, and it will make everything faster and simpler for the implementation. Now, while still talking about sending things, we can now send a file descriptor over the Unix domain socket without having reference count cycle issues. We have a lot to talk about there. What are file descriptors? File descriptors are pretty much a list of files that your task or your process has open or that it can write to. So those files will be listed in the system, and the file descriptor is the actual information on it. So if you were to send it to somebody else, he wouldn't have the file in and of itself. It would only have the address of the file and what you can do with it. So that's what a file descriptor is. Now, when you want to send those over Unix domain socket, now Unix domain socket are just pipes. So when you hear Unix domain socket, think a pipe to another process. So when you want to send your file descriptor to another process, now you're using a specific command. Normally with this, it's called scm writes, but we're gonna skip this. We don't need to know much about how it works. So when you're sending that to another process, normally you could have an issue where if one of the process was made in a specific way, it could mess around with the reference count cycle. And what it would do is that at the end, when you stop using this pipe and you would want to dump the pipe, pretty much just say, hey, I don't need it anymore. Well, the garbage collection code would look at it and it would say, hey, it's still open. I cannot dump it. It's used. And it wouldn't be used on both sides, but because there was a problem with the reference count cycle, well, it could never get rid of it. So now they have reworked the garbage collection code to make sure that this issue cannot possibly be made. So that's a great thing. We can have malicious code on both ends and still have thing works. Yay! Now let's continue and talk about basic support for packet forwarding control protocol. Now, what the hell is that? Packet forwarding control protocol is pretty much a way to talk with a 5G tower. Now, I don't think that it's in use right now, and it's pretty much a new way of thinking about things and to be able to communicate some data to the 5G tower. From what I read, it doesn't seem like it's not something that you will send all of your data to. It really just seems like I'm asking some status or I'm giving some information to the tower on how better to serve me. But anyway, my reading of this was pretty weird. I'm not sure that I understood everything, but now we have basic supports for it. And when we're talking about basic support, we're talking about really basic support. It only supports IPv4 right now. We don't even have IPv6, but it's a start, so we're happy to see it. And talking about protocols, we have TCP sockets that now supports SO peak off. SO peak off is a new command option that you can offset what you're reading from your TCP packets. So let's say that you receive a packet and you don't really need the 4 bytes at the start of the packet. Well, you can tell your system, hey, just ignore those 4 bytes and really start after those 4 bytes. So now I can use the command message peak to actually look at only the part that I need and not the first 4 byte that I wouldn't need. So that's fun that we have that new integration. So let's talk again about IO uring, which has a new operation, which is IO ring CQE fsock non-empty, which is fun because it can make sure that there's no connection request waiting on the socket. So if ever there's somebody waiting on the socket, you can now know about it using this command. So let us switch to Filesystem and block I/O devices. And let's start by something that kind of feels like network things so that we can fade it in and out. So we have the Linux Network Filesystem, NFS, server code that has now been changed. We're laying the groundwork for the future NFS-D CTL. What the hell does that all mean? NFS is, like the name says, a network file system. When you want to share some file with everyone, you can use its server code, NFSD, and share the files. Now, normally, if you would want to know the status of what's happening or you would want to change some configuration with it, you would normally need to change the config file. Now, what they're trying to do is to make some kind of protocol, some kind of system that you can use to be able to, on the fly, change the server configuration to be able to give you more flexibility on how you can manage the thing. So that's what NFSD CTL will be. So they're starting to put some connections. So they're starting to make netlink based protocols connection pretty much inside of NFSD, which will allow you to use NFSD CTL to manage how your NFS server code is running. Wow, that was a mouthful, but I'm sure that you probably either understood or are really didn't understand nothing. It's okay. If you didn't, you probably most people don't understand everything I say anyway, so good enough if you followed for all of this video. We still have a little bit to go on. We have the file system in user space, Fuse, that now get integrity protection support through FS Verity. FS Verity is a system that uses Merkle tree to ensure integrity on a real read-only file system. So it creates those Merkle trees and is able to say, hey, nothing has been tampered with, there's no corruption here, everything is good, you read the right data. So it's good to have this, especially in user space. It gives us a little bit more liberty. We also have OverlayFS that now can create temporary files using the OTMP file option. You might think that sounds a little bit useless, but that's actually something that is used in a lot of commands. So a lot of command will create a temporary file before dumping data on it. So it makes OverlayFS now a little bit more compatible. Now it wouldn't be a file system kernel update without XFS. So XFS has some standard change, like it gained more repair capabilities. As usual, it seems that every update is a gain more repair capabilities, but it has a pretty substantial change. It now has parent pointer. Now parent pointers are an attribute that were added to the in node. In nodes being index node, they're pretty much the part of the file system that stores permission and other relevant metadata. So when you use any file system on Linux, pretty much ext4, if you have, well, XFS in that case, you have your actual data of the file, and you have that in node that stores the permission and the metadata. So you don't have to search through your file to be able to know what the hell is going on with it. Adding the parent pointer to it actually allows for future optimization, like optimization in scrubbing, which is live repair of the in node, or in shrinking, or in a whole lot of other things that you can do with the file system. So just adding this capability will help us make XFS even faster, which is always a great thing, and it will allow us to still, again and again, give us the good old XFS gains more repair capabilities at every update. Now, we talked a little bit before about file descriptor. We have the new fdupfd query command for fcntl, which gives us a way to compare two file descriptor to see if they refer to the same thing. So we're going to be able to use those this command to compare the two and see, hey, am I dumb? Do I have 2 times the same thing? So it will make things faster. Now, we're talking about things that are faster, but some things are put into the kernel to make things slower. Now, we add a block throttling low limit mechanism, a mechanism that is there only to slow down one of your I/O device. We have that mechanism that has been removed because it was unused since its creation in 2017. So nobody was using it, so they just dump it. I mean, when you have something that is put into the kernel for, well, it's now been 7 years and nobody uses, we can pretty much infer that nobody wants to slow down their system voluntarily. Now, of course, it's been added for a reason, but nobody uses it, so we're happy. Yay, more free code. So let's talk about the enhanced read-only file system, EROFS, that now has the Z standard compression. Now, if you've seen my ZRAM video, ZRAM uses Z STD compression, Z standard compression. It's pretty much used everywhere because it's a pretty good balance of compression to speed of decompression or compression ratio. So it's a really great thing to have to your file system. So the enhanced read-only file system will now be able to use it. Now, for those who don't know why somebody would use EROFS, it's used often in phones because, well, you want to really make the kernel, well, the core of your phone, not necessarily only the kernel, but the system partition, something that you cannot write to, a little bit like the cloud natives implementation that we saw in the latest distro review. Well, if you want to freeze your system, you can use a read-only file system, and that's why EROFS exists. Now, we also have dmcrypt, which is an encryption device mapper. Let's just start by that. What is a device mapper? A device mapper is something that you put just between your I/O device, so your hard drive, and the data you're sending it to be able to do something to it. So you could be compressing it, you could be optimizing it in some way, or you can be encrypting it. So dmcrypt is there to be in between your device and your data to be able to encrypt it. You now have the option to make it high priority. Now, by default, it won't be high priority. The reason is that high priority is actually something that is only used by sound system on Linux. Well, now I'm talking about desktop, because on server, it's a whole other thing that dmcrypt being high priority is only there because of server implementation, because on a server, it may actually help us to make sure that the hard drive gets decompressed as fast as possible. But on a desktop, if your system prefers to decompress the data on your hard drive and not to play your sound, well, you're going to hear if your sound is 1 millisecond late. You're not going to feel if your hard drive is 1 millisecond late. So that's a good idea to be able to have it by default at off, but to be able to enable it for people that need it. Okay, so talking about enabling things, there's the performance tool, which is a profiler tool that is inside of the Linux kernel that is there to abstract away the hardware, so it won't look at how short something was to run, it will look at how many CPU cycles it used. So that tool has seen a lot of change inside it. Now, I'm not going to talk about any of it because those changes are way too complicated for my small human brain. So just know that there's been a lot of changes in that tool, and it's a really awesome thing to see. I just like the idea that you can have something that will count the CPU cycle that you're using to do something. It just seems insane in my head. Let's talk about memory changes. We have a vmalloc insane change on the last kernel, so on kernel 6.9, we had vmalloc that actually had a problem where if multiple core were trying to take memory from vmalloc, it would have only one lock file. So it had only one part that it could be locked and unlocked to say, hey, I'm using it, hey, I'm not using it. So because every core was using that same lock, everything would be slowed down. So remember what they did is they cut the memory into pieces for each core, and each core had its lock to make sure that nobody blocks one another. So that was a performance increase. Now we see one more performance increase on it. They found out that in the code, it was locking that vmap, so that part that is there to say if it's using it or not, it was locking it 2 times instead of 1, so making things slower. Actually, it was making things 4% slower, so somebody tested it through stress-ng, so we can actually see another benefit from a quick change in vmalloc. It's always fun to see when they have changes that carry over in all of the kernels. So one person does a change there and somebody else like, let's look at that code. Oh, there's something else to optimize. It's just cool to see. And talking about optimization that somebody saw and that reused old code, we have ZSwap that now replaces its red-black trees to store the data and now uses X-arrays. Now, let's just describe everything that's happening here. Red-black trees are a way to store data where when you're storing it, if you're not storing it in the right way, it will need to rebalance itself. So the tree cannot be, not balanced. So if there's an issue, it will rebalance itself and it can lend to slower performance. Now, X-arrays are a specific type that has been created for the Linux kernel that has pretty much the same performance of the red-black trees, but it doesn't have this rebalancing issues. So it actually gives us a little bit more performance. Now it's not big, it's less than 1% of a performance gain, but it's still a performance gain that may help some usage because, of course, ZSwap is like ZRAM, but on swap. So that's something that may give a little bit more performance to somebody in need. And talking about in need, everybody is in need of security. And we have some more security updates in the kernel. Let me give you some of the security update that I really like. One of them is that now you can have encrypted operation with your TPM device. Now, the TPM device is a chip on your motherboard or in your CPU that holds keys for you to be able to encrypt things with. So it's a special device that is there for security. It's used for, if I'm not mistaken, it's used in secure boot and in disk encryption if you really want that encryption to be solid. So it's used a lot. And it's really great that we have that, but now we can have encrypted operation to it. So even if you were to put some probes onto the pins between the TPM and the actual CPU, well, you wouldn't see nothing. So that's great to see. I really like those things that make it so our system don't even know what they're doing anymore. In the 6.9 kernel, we saw that we had a change from AMD that actually allowed you to host a virtual machine that you had no idea what was running on it. So it would run front to back encrypted, and you would have no idea what its memory was, what it was doing. So I really like those kind of changes, that it just feels like your computer has no idea what it's doing, but it's still doing it. I find it awesome. Now, they've also removed the crypto usage statistic. They found out that nobody was using it, and it was kind of reducing a little tiny bit the performance. Now, how did they manage to see that nobody was using this function? Well, somebody actually went through the sources of all the Debian packages. So they went through those sources. They did a source search, and inside that source search, they saw that it was only used once in pretty much an example package. So when the only implementation is the implementation to show how it works, well, you can say nobody used it. So another thing that was flush, now nobody needs to maintain it, which is good. Now we can also talk about BPF, that now has access to the kernel crypto framework. So if you have a BPF program, you can now use the kernel crypto framework, which is an optimized part of the kernel that's there only to encrypt things. So again, another way to treat data coming from BPF and to make it more versatile. We also have landlock security modules, which are security policies that helps you doing things like sandboxing, so you could tell a part of memory or a program to be limited in what it can do. Now, it now applies to IOCTL, which is pretty much a system call that is there to modify files and file descriptors. So, well, in my mind, it seems self-evident that if you want to apply security policies to a program, you would need to make the part of the program that can write things on some files to not be able to write things on files at places that you shouldn't want to. Anyway, I'm probably not smart enough to understand why that wasn't done in the first place, but now it's done and it's great. But something that I do find pretty smart is the new boot option, the init mlock on free, that will zero out any memory that 1 has been mlocked and 2 hasn't been mem unlocked when a program crashes. Now, mlock is a way that you can make sure that nobody touches your memory, so you can freeze that memory, nobody can look at it, nobody can write on it, it's mine. And munlock, of course, is the reverse of that process. You can now say, hey, it's free, everybody can look at it. So the reason why this boot option is important is that, let's say that you have a key manager, so it's a manager with or a password manager. Let's make it simple. So you have a password manager, it contains all of your password, you put your password in it, so now you have all of your keys that are de-encrypted, you have all of your password that are de-encrypted and in memory. Well, of course, your program is really well made, your password manager is really well made, so it mlocks the memory, nobody can look at it. But what happens if your program crashes? Well, now you can have a really bright hacking program that's like, hey, I'm just going to snoop at that part of memory because he was there, so now I can actually see your password and your keys. And if the program was even smarter, it could attempt to crash the program itself and then try to scoop around the information. So to prevent that type of attack, to prevent that issue, the boot option allows us to zero out the data that's in the memory if it crashes. So if you crash and you don't munlock beforehand, well, it will put 0 in memory, making sure that nothing can be read by an attacking program, which is really awesome. Now, let's talk about something that isn't really awesome. So I've talked a little bit at the start about prison letters. Yes, we have a prison letter from none other than Hans Reiser. Now, some people may recognize that name because he is the lead dev of ReiserFS. Now, for those that don't know the whole story about why we don't hear about ReiserFS that much, is because, well, the guy was convicted of murder in 2006 because he murdered his wife. So, yes, cool. So what happened is that this fine fellow decided to write a present letter saying, hey, I think we should make sure that the readme that I did, that was pretty much trashing a couple of people and saying that some people were, let's say that there were some not so fine words inside of the readme because some people, quote unquote, betrayed them. Let's say that we could remove that part and change it to something a little bit more wholesome and make that right before we phase out the RiserFS code so that we don't have this immortalize in the last kernel that's going to use it. So that's actually something that some devs did, actually change the code to make sure that the insults were out of the README file, and that also implies that we will not see RiserFS in the next release. So it's the last release of compatibility for RiserFS. So yes, that's how Prison is related to the kernel on this kernel release. So that was the last commit that we're going to cover today. Of course, there's more that I haven't covered, but some that I find just boring, so I'm not going to talk about them. But still, great work from the Linux devs, and I want to thank a couple of people that, well, without them, I couldn't be making this video. There's Linux Weekly News, there's Phoronix, and there's Kernel Newbie. Without those websites, without those people, I wouldn't be able to have as much information needed to make those videos, so thank you a lot. And lastly, I want to thank the people that, well, were there for the whole hour, because I mean, that's an hour of hearing me and probably being pissed at my voice, but if you enjoyed it, I'm very happy. That's flattering. Thank you. Leave a like, leave a comment, and share, because of course if you enjoyed it, probably more people will do. So thank you a lot for being here, and of course, as usual, take care.